Hello, everyone. Today we have Mukund, a long-time collaborator of mine, visiting us after a few years. And so he'll be talking about our work with various other people.
Good, thanks, and it's great to be back after nearly 5 years. So I'll tell you today about something I've been doing mostly as a pandemic project, more or less, with Loga and various other people, which should hopefully get summarized in a paper with our postdoc Julio Virueta sometime next week. So I'm going to give you a broad brush. So there are many papers with many people, which I'll mention the details of, or at least the broad sketches of as we go along. But I want to give you a sort of first broad picture of what is it that the program we're after is trying to achieve, and what we've managed to do so far and what's left to do. So there's sort of three broad motivations depending on your perspective for this sort of program. One is to just understand black hole physics, especially thermality of black hole physics, from a Lorentzian viewpoint, from a real-time perspective. So we don't want to start with the Euclidean path integral and derive black hole thermodynamics, but we would really want to be able to compute real-time correlation functions, in particular capture both the physics of dissipation into black hole horizons and the associated fluctuations a la Hawking of those dissipative quanta. A second, which is close to my heart and something that, again, we spent a long time with Loga trying to work out, is to derive, using ADS CFT, a fluctuating, an effective theory of fluctuating hydro using holography. So again, here we have lots of data to go by, starting with old work from nearly 2 decades ago of Polycastro-Son and Starinets, who showed that response of black holes in ADS has hydrodynamic characteristics, to something that happened a few years later, which was to show that perturbations of black holes can be recast in nonlinear form as the equations of nonlinear hydrodynamics, to the work that was done by myself, Loga, and Felix Hall, and also by Hong Liu and collaborators, and by Christian Jensen and collaborators, of constructing from first principles an effective field theory of hydrodynamics. But those were formulated on some symmetry principles which made some assumptions, and one would like to check if in a context where we have control from black hole physics, you can derive that kind of effective field theory without making those assumptions. The third motivation, which is really what the title is about, which both of these sort of fall under the same aegis, is to understand dynamics of open quantum systems beyond quantum mechanics, really in quantum field theory. And this is what I'll try to primarily focus on, although as I go along, I'll touch upon both of these points, because you'll see that what I need to do to address point 3 is in part tell you how to solve point 1, and along the way tell you something about quantum systems which are interacting with degrees of freedom that are long-lived. It's sort of related to point 2. So Goldstone modes are an exemplar of Goldstone modes, which I will take in this talk will be hydrodynamics. So we'll sort of work backwards in some order in this list of motivations. So if you've been around Loga, you probably have heard all that you need to hear about open quantum systems, but let me give you a brief motivation if you haven't. So what we have in mind is some environment, which I'll call E, and some system, which I'll call X, which are coupled in some way. And the dynamics is some kind of unitary dynamics on the combined system environment density operator. So there's some Hamiltonian that's prescribed, and it involves both of these in some unitary way. If I integrate out in the environment, then what I'm left with is a density operator on my system X, but this doesn't evolve unitarily. This evolves by what's called a quantum channel, some trace preserving map. So which is induced by the unitary evolution upstairs. So let me just call it some channel which is dictated by the environment, which tells me how my density operator evolves. So this part is reasonably clear, because if I want to ask questions about what the channel is, I can go upstairs and ask. But typically, we're not interested in keeping track of the microscopic details of what's happening in the environment. We just want to integrate it out and write down the effective dynamics. So in the language of path integrals, this problem solution to this problem is well known, and this was already addressed long time ago by Feynman and Vernon. So if I take my environment degrees of freedom to be some variables, let's call them psi, and I have my x degrees of freedom, and I start with some action, which is the action for the individual pieces plus the coupling that which is involved. So that's what you would write down if the combined system was in some pure state. If your combined system already starts in some density operator, I have to double this path integral to allow for both the bras and kets. But let me just schematically write that at the end of the day, what I know is that X, the system itself, has just a density operator. So I have to keep track of both the bra and the ket part of it. So I'm going to write a path integral for it, which captures both these bras and kets in terms of two double degrees of freedom, which would be the part that's sort of factorized coming from the environment independent interactions, and a new thing which comes as a result of tracing out the environment, and which in the language of Feynman and Vernon is the influence functional. So this influence functional captures the non-trivial information about what the environment has done, and it captures both it's constrained by the microscopic unitarity, but it's not necessarily unitary because it's captured in the physics for quantum channel. So the question really is, what is the effective field theory of this guy? And to some extent, in simple systems, quantum mechanical systems, this problem is well studied and well understood. And this, for example, the physics of a single particle probing a thermal medium, a Brownian particle, which obeys classically a stochastic Langevin equation, can be derived by thinking of a Gaussian system where you have a harmonic oscillator probing a bath of harmonic oscillators. This was famously worked out by Caldera and Leggett in the mid 80s.
Sorry, basic question.
Yeah.
How is the non-unitarity reflected in the functional?
In this functional? So this guy is going to have explicit imaginary pieces. Okay, so there's going to be explicit dissipative pieces. So if I could just write down, for example, the action for the, so if you start with the case where you have a single oscillator coupled to bath of oscillators. So let's say the bath oscillators have some intrinsic dynamics, and then you have some, let's say the oscillator we are probing is just a free particle, not even an oscillator, and then you just have some linear coupling. So this is the temporal dynamics of the unitary dynamics of the combined system, but the effective action for X has explicit imaginary pieces. I'll tell you what these subscripts are in a second. Where? Sorry? Sorry, these are X. Yes. I am mixing my X's and Q's. And X, A, and D are just these combinations. But you see, the presence of this piece is signaling, and presence of this dissipative piece is signaling the fact that there is non-unitary. And this piece is the piece that says that non-unitary dissipative piece comes with an associated quantum fluctuation, which is a noise term in the problem.
The fact that it is dissipative,
yeah,
is something that is put in or it comes out?
It comes out. It comes out because of this linear interaction. It's not something that you have to put in. Basically, it's the same, the logic behind it is the same logic that you would have used to argue for the Brownian motion in the first place.
So somehow the information that the environment is much bigger is going in somewhere, right?
Yes, so it's been assumed that the environment is a lot bigger than the system. Although it's not necessary for the environment to be a lot bigger, it just needs to be at least as big as the system, as you can see from the end result.
I'm just wondering that, the imaginary piece means time reversal symmetry, right?
Yes.
So somewhere the original theory this the system didn't have. And so somewhere the fact that it's dissipative and not growing, for example,
yes,
has gone in that information, right?
Correct. So the time reversal is broken, but in a very particular way, that it's dissipative and not anti-dissipative. There's a sign to this gamma. Yeah.
It is put in or does that come out?
That should come out as a consequence of microscopic unitarity. So it's a corollary of, in some sense, of the fluctuation dissipation theorem. So it's not something that has to be, if you put that in, then you would not be sensibly deriving an effective field. So this is one of the challenges of trying to derive such.
Two harmonic oscillators coupled to each other.
Yes, because so my intuition for why that should happen for even two harmonic oscillators is that at the end of the day, what this is capturing is the fact that the environment is entangled with the system, and the lack of unitarity down here is simply that you're building up entanglement, so you're losing information to the environment that you're not keeping track of in just your system. If this unitary was factorized and this density operator was factorized, then you just get unitary evolution everywhere.
I guess it should be true that the path should have kind of harmony. Things should die down. Those things you need to have to get a local.
No, the locality is one thing, Loga, but there's also a question of whether the sign of the dissipation is fixed one way or the other, even if you have a non-local system.
I'm just wondering that the fact that it's dissipation, normally it's that you have a big path, and so information can get lost, right? But if its path is not big, then it can also gain information. That's what I'm wondering. Little worried about. What is, I mean, destroys this time reversal.
Yeah, it's true that all the derivations that I know of assume the path is much bigger, but it is in conflict with the intuition that I have that the amount of entanglement you can build up is capped because of entanglement monogamy. Once this single particle gets, say if you have two particles, and once one of the both particles get maximally entangled, there's nothing more. You can keep adding other pieces to the environment, but that just redistributes the entanglement. So that's the reason why I said you don't have to make this environment a lot bigger to capture this physics.
Somehow the original system, if you change t to minus t,
it
remains unchanged.
Yes, the original system was time reversal invariant, it had some unit.
Here, t to minus t symmetry is good, right? And
yes.
One should be able to understand that from first principle, right? Exactly where this breaking is happening.
Yes. So, I mean, to be fair, in many of our earlier derivations of effective field theory of hydrodynamics, we made an assumption of how that breaking happens. And we showed that that is consistent and leads to something like a second law, so which is basically constraints signs of these coefficients.
Okay, what is F in brackets? F in brackets.
F in brackets, that's just gamma over m beta. That's just a noise term. So this noise squared is related to fluctuation dissipation. By fluctuation dissipation to the temperature of the body.
Gamma is just a simple function of the alpha.
Gamma is just a simple function of alpha. It's some parameter that determines what the coupling was. Yeah.
So the fact that this channel is phase preserving.
Yeah.
That has to go in somewhere.
No, I mean that is sort of, if these were normalized density operators, I'm just tracing out. This is a trade. Then this. Yeah. So that's the sort of statement that the density operator just evolves in some quantum channel. Was there some other question from the Zoom?
Yeah, I have one question, Mukund. Can
I
ask? Yeah. As Ashok was asking, so in the Markovian limit, generally in open system Markovian limit, you just get the dissipation, but if you have a non-Markovian where you allow for back reaction, then you also have an oscillatory thing to happen, right, in a simple quantum system. But somewhere you have taken the Markovian limit here, right?
In this case, I did, but I will talk about systems which have long-lived dynamics in a while, if you hold on.
Okay.
Anything else? Okay. So I want to do some exercise of this kind, but in a setting where I have some control, and that's where we'll talk about holography. And part of the intuition, which again, although despite what I just said in response to Ashok, is coming from the fact that holography provides environments which are thermal, and in most generic cases, both fast scrambling and largely dissipative. So they're sort of very good thermal environments to try to study. So this is sort of backwards from what most people want to use coupling systems of holography want to do, where they want to couple some bath and extract radiation. We want to do exactly the opposite. We want to integrate out the holographic CFT at the end of the day. So the kind of system I want to study is, to be very specific, let's just say I want to study n equals 4 Young Mills at some temperature, inverse temperature beta, coupled to some field x. You can just take this to be a free field in 4 dimensions, it doesn't matter. And we'll just have some coupling of X to some gauge invariant single trace operator of n equals 4. Okay, so that's our paradigm. So it's very much analogous to this guy where I've replaced all these Qs by a strongly coupled field theory, and I've replaced this linear coupling by some single trace operator of the field theory. Yes, so I didn't say, but the initial state here I took to be rho beta of Q, tensor with vacuum. Thanks. Okay. So again, I'll take the initial state to be rho beta of n equals 4. So the thermal state at some inverse temperature, tensor with some, let's say, vacuum state for this field X. So again, what I want to do is I want to be able to start with this parent Lagrangian and integrate out to n equals 4 degrees of freedom. I'm going to be working in the strong coupling regime where this part is really a black hole in anti-de Sitter spacetime. Okay, I'm cheating because I won't talk about the global black hole. I'll change my picture in a while and just talk about the planar black hole. Okay. So I'll talk about translational invariant systems, but there's some horizon size which is related to inverse temperature. So what we want to do is so if you look at this action, as far as the n equals 4 theory is concerned, X is just a source for the operator O. So if I want to study physics of what happens, I could first start the problem by computing the generating function of correlators of this operator O, and those in turn would feed in the effective action for X and give me what, when I'm integrating out the n equals 4 degrees of freedom, that I could just to leading order and amplitudes use that as my effective action for X. The main difference is I don't want to run this calculation in Euclidean signature, which is what one often tends to do when computing correlators, but I really want to see this real-time perspective so I can keep track of both the dissipation and fluctuation. Okay. So statement number 1 is that S effective X can be obtained from the generating function for O correlators where I just setting J equals X does the job. But what we want is not the regular Euclidean generating function, we want the real-time generating function. In field theory terms, this is not sort of hard to compute or hard to say what to compute. So we don't want to compute this on a standard Euclidean contour, but rather we want to compute correlators of O on the Schwinger-Keldysh contour. So this is 0, this is I epsilon, this is I beta. I put my minus signs. And I want to compute this on some contour that runs forward and backwards in time. So we want to compute O correlators on this Schwinger-Keldysh contour, which allows us to extract causal correlators and associated fluctuations. And here already let me presage that answers so I'll tell you in a minute how to go about computing this, because that's going to be part of the discussion. So that's going to address this first motivation. But let me touch up on the second bit for a second. How we are going to treat this problem very much is going to depend on O. So, and one way to tell this is to go look at the retarded response, just compute the retarded correlator for O in this background, which people have done over the last 2 decades. And you see that there are two kinds of O operators that we have to keep track of. The first we'll call Markovian. They are ones whose retarded response is characterized by a Green's function that's meromorphic and has poles in the lower half plane. So this is the pole structure G retarded function of omega and momentum, except that these poles are gapped from the real omega axis by an amount proportional to inverse temperature, proportional to temperature. Okay? So these systems have gapped quasi-normal modes. So they have so in real time, these modes decay within a thermal time scale. So that's in keeping with this intuition that things are Markovian, things decay very fast, and you don't have to keep the integrating out this holographic environment is something that one can do because there's no long-term memory in the environment.
So Mukund, just one clarification. Are you computing at late time after you assume that the thermalization has happened and then you are calculating at the late time, right?
Well, I'm in an equilibrium state, so I'm not quenching the system. My n equals 4 state was prepared in the equilibrium thermal state. So I prepared the state at time 0 in the thermophile double, but not really the thermophile double because it's really a thermal density matrix in one copy.
But I thought you wanted to consider open system where system will go to eventually thermalize. Is that not the picture?
No, I want to compute the effective action for the open system, but the effective action for the open system cares about the equilibrium correlators of the n equals 4 system. N equals 4.
I see.
Yeah, I'm going to integrate out n equals 4 in some Wilsonian sense, and for the purpose of integrating out, it's sufficient to worry about this just the equilibrium correlators.
Okay.
So X is not quenching in any sense. X has some temporal dependence, but I just want to extract what its effective action is. So the fact that I drew one set of pictures means that there's another category, and like all other categories, it's what it's not. So it's not Markovian. And in this case, the quasi-normal spectrum is not gapped, but has a gapless mode in the problem at low frequencies and low momenta. Okay, so let me be precise. So a gapless mode, by which I mean omega of k goes to 0 as k goes to 0. In most holographic systems, there also exist very long-lived modes at high momenta. So high out here, even this generic operator does have Green's function, does have poles whose imaginary parts are small if the momentum level is large. They're just saying they're projectiles that are just whizzing past in the plasma, and they don't see large dissipation. Okay, so it's very easy to see this it's much easier to see this in the global black hole. In the global black hole, you have orbits. So if you're sitting on an orbit far away from the black hole, you're sort of very close to the boundary, and those geodesics tend not to decay, they give you long lifetimes. So large angular momentum geodesics or large momentum geodesics have very small quasi-normal modes, they're exponentially small in the parameter. That's not what I'm talking about. I'm talking about gapless modes that sit at low frequencies and low momentum. And these typically happen for conserved currents. Okay? And these are the class of operators that if you couple your system to will lead to long time behavior, which is problematic from the point of view of integrating out because there's no locality in the effective action. Okay? We'll address that in time to come. But first, let me now go back and try to motivate how this works. Okay, so that's going to be next half an hour or so, just telling you how to, roughly speaking, take this contour as the boundary contour for n equals 4 Young Mills, fill it in with some bulk solution, and compute correlation functions consistent with Schwinger-Keldysh and KMS.
I have one question, quick, just one simple question.
Go ahead.
So suppose I take, rather than this n is equal to 4 Young Mills, I just take a simple open quantum system, one-dimensional open quantum system.
Yeah.
Then I know that this open dynamics is governed by this Lindbladian operators, right?
But that makes some assumptions, right? So that Lindbladian operator is assuming some kind of Markovian behavior.
Right. Some kind of Markovian behavior, as well as you can also do some kind of non-Markovian things also in quantum open system. Yeah. But Lindbladian do have a spectrum, a particular spectrum, which is like this your retarded thing, only one side of it, which gives a dissipation kind of thing. Would these correlators be evaluated? Would there be any relation between those spectrum and this Quasimodo mode? Is there any relation?
I think there should be, but I have not thought this through carefully to say definitively. I mean, it's true that the Lindbladian has a little bit of non-unitarity, and that non-unitarity is related to the dissipation. Here, these correlators do signal that dissipation. So yes, in
the picture that the non-Markovian thing, there's a long decay thing. Rather than decay, there is this oscillatory thing that you have, like basically at the zero mode that you have. So that also is very related there. In the non-Markovian, it just doesn't decay because there's always a backflow.
Well, here it's not oscillatory. It's a very slow decay. So it's not local in the effective action. We'll fix the non-locality, but. Okay, I'll leave that picture there because I'll use it later, and then get to this business about how to compute correlators. So historically, at least, I find it surprising that the rules for computing correlators in ADS were the first things we learned, the GKPW dictionary, and it's taken roughly order of 2 decades to write down similar stories for at least equilibrium systems in real time, and not for want of trying. So the question really is this: I start with n equals 4. I don't have the standard real-time Euclidean contour, or I don't have the standard Lorentzian contour, but I have this Schwinger-Keldysh contour, and I want to ask, how do I fill this in? What geometry fills this in consistent with the Schwinger-Keldysh rules? And there's an answer, and I'm going to draw a picture and just motivate the answer, which post facto will be justified. Okay, this picture needs to be viewed in one higher dimension, but since this is all I can draw, you're going to have to bear with it. Okay. The bottom is a Euclidean cigar, which is dual to the Euclidean black hole. That is used to prepare the state in the far past. I then slice open that state with an I epsilon, evolve one half of it forward and the other half of it back. Okay. Now, the two halves are pinned at the tip of the cigar, which is the bifurcation surface in the Lorentzian section. And I'm smoothly continuing the tip of the cigar to future infinity. And it might help if I draw a picture of the following kind. So this should have been a picture for an eternal black hole. So if I prepare a state at time 0, I look at just this slice of it, this one half of it, which is the slice that goes from here to here. And let's take this to be the ket part, so that's right, this is left. And things are falling in. So on the back side of this picture, things are falling in, and then they sort of loop back out through this fold. And that means that stuff that falls in comes out like this, another copy of the same thing, but all I keep of these Penrose diagrams is these regions. Okay. I'm not keeping the thermophile double, I'm folding on the horizon. Strictly speaking, it's better to describe this whole construction without thinking of an explicit fold that runs along the null surface of the horizon by a small epsilon deformation, and we can do that. So this is the horizon, this is infinity. If you go look at the, say, the tortoise coordinate, the integral of the metric, so the metric for the black hole, which I'm going to use ingoing coordinates in ingoing Eddington-Finkelstein for translation, and I'll just talk about translation invariant systems. So the tortoise coordinate R star has a logarithmic cut, and I let the cut run from horizon to infinity, and instead of complexifying in the boundary, I've complexified the temporal coordinate because I've taken the contour and made it run with an I epsilon to go from 0 to I beta. I'm not going to make the time coordinate in the bulk complex, but I'm going to jump over this cut over a keyhole contour. So in other words, the claim is that you can make the claim in either two ways. Either there's a complex geometry, which is the filling of the Schwinger-Keldysh contour, or insofar as bulk integrals are concerned, you compute them by starting with the usual Euclidean integral and contour deforming them to come and lie in the Lorentzian section on this contour. Yeah. 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 I haven't told you that yet, but wait for it. No, so I haven't told you the boundary conditions. Hang on for a second. So all I'm saying right now is that you keep this future domain of outer communication. You keep this domain of outer communication, time reversed. Stuff that falls in, so to speak, just emerges out. Okay, so I have to tell you what emerges how. Okay, so that I haven't told you, and I haven't told you what boundary conditions put where. Okay? But that's what I'll prescribe. On this contour, what would you do? You would put operators at various times. So you can think of time, the Lorentzian time running this way. And this is some time you can put various correlators at various times, and those will compute various time orderings of correlation functions. So that in particular means you're turning on various sources. You can do the same thing here. So those are like turning on non-normalizable modes for the corresponding operator on the boundary. You sprinkle sources here, and we have to solve the corresponding bulk problem with these sources fixed. And once you have fixed those two sources, there is no boundary condition to impose on the horizon. Okay, so you have to find out how to solve the problem. How to solve, for simplicity, the double Dirichlet problem on this geometry with sources specified on both this left and right bound. It should be smooth because I've deformed the contour to not go through the horizon locus, but rather I've keyholed over it, so that contour deformation gives you something.
I have the opposite. I can understand.
You can explain to each other. Yeah.
On the right hand side, I want to do a calculation. When I do some sources and conditions on the right boundary.
Yes. Yes.
I put some boundary conditions, and I still didn't understand how those are related to the other horizon. But maybe for later now.
I'm still not coming there. I'm not told you yet, but I'm going to tell you. Yes, Rajesh.
No, so the right one, this whole thing exactly. You
Mean by it. So, instead of doing radial integrals along the real axis, I've let the cut run along the real axis.
So you're saying radial integrals when you compute some
Bulk correlators. So bulk to boundary. I'll first define a bulk to boundary propagator, and then I'll try to compute Witten diagrams, and all those diagrams will be computed using this on this keyhole contour. So radial integrals dr will get upgraded to this contour dr.
This is a prescription.
This is a prescription.
Equivalent to that geometry.
That is equivalent to that geometry because I'm avoiding the horizon. So the null cert. Yeah.
We see the picture.
Yeah.
As a kind of a radial cross section.
Yes, exactly. So all I've done is instead of two sheets meeting at a null surface, I have gone out in the complex plane and come around the null surface. So it's like jumping light cone cuts. You jump light cone cuts by going around them one way or the other. I've picked one way to go around them. But it also picks up monodrome. There are modes which pick up monodrome. Yes. So if that was the story, then there wouldn't be Hawking radiation. Yeah. Okay. So indeed. So let's address Surat's question because that's the important point. And I didn't emphasize, but I already broke time reversal symmetry. I'm working in ingoing coordinates. Okay. So let me say the following. You first solve. So I'll just give you an algorithm. Okay, I'll give you the algorithm, and then we can figure out how to solve the problem. So statement number one is you solve the wave equation for, let's say, for scalar field. So probes. So let's say O n equals 4 is dual to some field phi in the ADS. Maybe it has dimension delta. So you solve the scalar wave equation. Which you can write down. Okay, I'll write it down in a very particular way, and you'll see why. And I'll work in momentum space. So this is, I'll write this as big N equals 4. With this derivative d plus is some derivative that takes into account this non-orthonormal basis. So it's basically some combination of time derivatives and radial derivatives. So it's a basis that's sort of adapted to the non-orthonormal coordinates. And so what we'll do is we'll solve the scalar wave equation with ingoing boundary conditions and define what I'll call the ingoing bulk to boundary propagator. So this will be some function of omega and k, which satisfy the boundary conditions that it's normalized to some source which I'm setting to 1 on the boundary of areas, and it's regular on the horizon, it's analytic on the horizon. And in these coordinates you can check for any black hole, the analytic solution is just a constant. What? Yes?
What R square?
At the horizon? No, don't need it because the Gn is just constant. Mode in the mode function, the horizon are constant. This. Then let's come to your question. So maybe the easy way to say it is this. If you go look at any black hole solution which has a non-degenerate horizon, the statement that a black hole is thermal can be seen by in the wave equation as follows. In these coordinates, the horizon is always a regular singular point of the differential equation. So it has two characteristic exponents. One of them, because I've chosen ingoing coordinates, is 0. The other is I omega. So local solutions are r minus r plus to the power 0. That's the constant, which is why I said this. And the other solution is r minus r plus to I beta omega over 2 pi. Okay. So for generic omega, this guy has monodromy. So the statement is, as you go around, you have to pick up that monodrome. Okay. So the outgoing solution basically goes from ingoing to outgoing coordinates. In usual language, you would have just go from with a half, but that's in Schwarzschild coordinates. I mean ingoing coordinates. I removed it's so yeah. So I removed t. It's t plus r star, and when you go to t minus r star, you get this other piece. Exactly. It's just changing ingoing to outgoing, but in particular, there's a particular monodromy you pick up as you go change from ingoing to outgoing, which is the I omega. Yeah. Yeah. So if you're happy with that, then it's very easy to say what the other solution is. The other linearly independent solution is the outgoing solution. And so there is an outgoing propagator, which is given by time reversing the ingoing propagator and putting a factor where the zeta is being chosen. I'll get my factors wrong in real time, to be the tortoise coordinate with monodromy set equal to 1. Okay, I might get even this right in real time. Okay, so that picks up the monodromy. And now the general solution, of course, is just some linear combination of these two guys. And now you can go and ask for the general solution to have source on the left boundary or on the right boundary, and just solve for it as a function of the sources, and here's the answer. Okay, and the fact that you pick up these monodromies basically give you these statistical factors, which is not at all surprising, because this is exactly how Hawking's calculation is supposed to work. I'm doing translational invariant systems, so all of these are taken into account because the K just appears. Everything happens in roughly the two-dimensional RV plane.
It's a scalar field.
It's also scalar. It's also scalar field. There's no spin. Yes. So the phase, yeah. No. So this is a full solution with sources turned on. Okay, but now you can go to town with it, because you have the general solution. So, and you have it in terms of bulk to boundary propagators. So you can just start drawing Witten diagrams here. There must be some color. Yeah, go on. Yes. Yes, and on this boundary. Correct. Correct. With respect to the sources, yeah. So you just now you have a solution. You just plug this into any action you want, and then you just evaluate. But that evaluation we can do diagrammatically, because that's exactly the Witten diagram prescription. So I'll just draw pictures of diagrams. This guy is this guy, and the thing behind is this guy, and the thing in front is this guy. The Euclidean thing is just preparing the state. Yeah, this is just I told you this is mixing metaphors, because this is Euclidean, that's Lorentzian, so it's not supposed to be drawn this way, but I can't draw any other way. So now we just have, say, bulk vertices, and then glue them various ways, and maybe you even have a bulk to bulk propagator, 4-point exchange diagram. It's not going off this surface, it's just on the surface, but it just. Okay. So again, you can write down the bulk to bulk propagator. Was there a question? Yeah. So this guy also you can compute because you can use some standard Wronskian trick to compute it. And let me write it in a particular way. And then, okay, let me put in quotes here, G in, G out, theta functions on this radial contour. Technically, there's some other linear combination of G in, G out. I don't want to tell you what that is right now. But the important fact is, given G in, you can just build this. And this prefactor just comes from some Wronskian calculations. But this prefactor also has a phase. This is important. Okay. So now, any calculation, as Subrat said, is just take all this data, take phi, take these G bulks, put them together as you would in any regular weighted diagram, and do the contour integral.
So this is the thing. This is this bulk to bulk propagator is the smooth one in this geometry.
Yes,
that's
how we define it. Yes, yes. So, well, we guess it two different ways. We decided to get a bulk to bulk propagator that was purely normalizable on both ends. So that's why I put quotes here. So there's some linear combinations involved to make it normalizable in both ends, because G in and G out are not normalizable. And it's smooth. It picks up the right monodromies as you go around, and it satisfies one important condition that I'll tell you in a second. Okay. But the fact that it solves the bulk equation with the delta function source is pretty much guaranteed by this Wronskian construct, by this variation of parameters construction. This theta function, when it's differentiated, gives a delta function. Standard trick to construct Green's functions. Okay. Good. How do we know this is all right? Okay. So this is related to the question. And what you have to check is, if you, for example, turn on the same set of sources on the right and left, you're doing nothing. So correlator should vanish. If they're at the same times, if they're sort of balanced, if the same unitary evolution forward and backward, then nothing happens. This whole thing can be collapsed back. Yeah. I do the same forward evolution and undo the same evolution going back with the anti-unitary. So nothing happened because U dagger is 1. Yeah. You have change sites or temporal positions effectively. Yeah. You have to unbalance them. The other thing, which is not manifest, is that you can take operators here and you can take them through the Euclidean circle and bring them up here. So that gives you KMS conditions, which tell you that there's some underlying periodicity in Euclidean time. So both of those things should work. And there are many ways to do this, but let me give you one basis, which is a translation of the right-left basis that Loga and Soumyadeep worked out a few years ago. Let's see if I get this right. Okay, maybe it's easier for me to look it up. Sorry. Let's see. So it's basically given by some combination of Bose-Einstein functions. I'm only talking about scalars. So in this basis, the statement is that any correlator with just F's or just P's vanishes. And only the mixed correlators survive. And one way to confirm that everything we're saying is correct is for us to do these contour integrals and check that that is true at every order, for every endpoint function. So for contacts, the argument is very, very easy. We already showed this in a paper 2 years ago with Chandan. And for exchange, this is something that Loga worked out with Godwin, and we sort of worked out in this upcoming paper. So for low point, up to 5 and 5 point functions, yeah. Okay. Yes. So you're right that since we are doing a Euclidean equilibrium state, you could just compute the Euclidean correlators. For every one of these FF sequence of F's and P's, the answer is some nested sequence of commutators, anti-commutators. The correlator translated into ordinary left-right basis or just ordinary correlators is just some. It's like a retired Green's function. It's either the commutator with the theta function or the fluctuation guy, which is an anti-commutator. So it's some generalization of that to higher point function. Coming. So in the boundary, you could just do it. And to compute any of those commutators or anti-commutators, you just do some I epsilons. So given the time ordering, which is basically all this sequence of F's and P's is telling you, there exists some number of time orderings of I epsilons. And the number of I epsilons you can check is consistent with the number of ways you can put sequences of operators on the Schwinger-Keldysh contour. So things that you can't put in the Schwinger-Keldysh contour, you can't get from those time orderings are not part of this discussion. So those two would certainly work. As far as I know, nobody has done even simple correlators, things which are known analytically, for example, by analytic continuance. 2-point functions, various people have done over various years. I think in 2D CFT, Gapsar did this first way back in the 90s. But 3-point functions, there is some half I epsilon discussion in the last decade. I think the Baker, one of the Bakers did it with some student. And you can check that it of course gives you the answer, but I just wanted a Lorentzian prescription to get it. What you're asking is, can I start with the Euclidean Witten diagrams on the cigar and get here? I believe by virtue of what I said about the field theory, it must be true. And I did try to see if you could just take the Euclidean Witten diagram and show that there's a contour deformation that gets you here. I sort of have convinced myself that yes, it's possible, but technically I've not been able to show it. So, I mean, at a conceptual level, I totally agree with you that there should be nothing new. And if you do that, you derive this contour prescription. Okay, because right now I'm taking this as an input and checking that it's consistent with everything we know from thermal field theory. That's it, sort of raison d'etre, so to speak. But I haven't. No, but you probably mean you guys did it in for the vacuum correlators. I wanted thermal correlators. Uh-huh. Yeah, Yeah, I mean, the thing you want to really check is this, that you sort of satisfy the, I mean, it's sort of obvious that they will satisfy KML because the Euclidean correlator are periodic and things of that kind. Sure. Yeah. Okay. Let me tell you something about domains of analyticity afterwards, because there is a catch. You have to derive something else here. Maybe I'll just say the Euclidean domain of analyticity is this strip, some strip of width I beta in frequency domain. It's in this theory, it's possible that you get quasi-normal modes in that strip. They're not visible in the Euclidean domain. You have to get those after analytic continuation. So the Lorentzian correlator is only analytic. The retracted guy is only analytic in the lower half plane, in the upper half plane. So it cannot pose all the way up to the axis, and it does. Yeah, that is just true here too. So I mean that's sort of true from. It's actually not manifest, but this is how Loga and Someri constructed this basis. Okay. Okay. So the rules are in place. You can compute, and I emphasize that you can compute as many Witten diagrams as you want in these geometries. It's no different now than the standard computation of ADS correlators. So if you have some generic Markovian operator, the problem is very straightforward. You just compute and then just get the generating function and just replace the sources for the probe systems field. What do you do for these guys, which are not local? Okay, so you can compute the generating function. The generating function, the correlator, the TT correlator has poles. So if I look at T0I omega k, T0I minus omega minus k, this guy has a pole. Momentum diffusion with D is proportional to the shear viscosity. This is how Polycastro and Sorinets did deduce that there is hydrodynamics, and they obtained the famous shear viscosity value. If you compute the energy density correlator that has a similar pole, but now there's a physical phonon, so the dispersion is omega goes like yes, Rajesh.
So are you saying that this prescription doesn't work for such operators?
No, the calculation works, but if we now try to take the generating function of these guys and use that to build the effective action for this field that we were trying to write down, that effective action won't be local, right? Because it's just a statement that you have singularities without gaps at low frequencies. Okay.
It won't be local.
Yeah. But there's no problem calculating the correlators. Correlators are well defined. Right.
And they give the right generating function.
They give the right generating function. Correct.
It's only for the effective action.
Yeah.
But that's, I guess you're kind of integrating out some.
Yeah, exactly. We're integrating out massless fields. So we exactly have the problem that we have non-locality in the standard Wilsonian sense that we are supposed to not do this. The cure is a standard cure. Don't integrate these out. So yes. We don't know. Well, that's the correct answer. it's easy, at least I think various subsets of us have worked out what boundary condition, what kind of monodromies you pick up. And we don't have a simple contour prescription, but we can work with multiple sheets of the geometry. And I can tell you what the jumps are. And we can check that the 2-point function level, you get the right answers. So it very much helps that there is a nice basis, this kind of basis that extends, and you can just check in that basis. So yes, in principle, that can be worked out. What can correct me, but what we've never been able to show is that gives you sensible connected higher point correlators. So even for contact, forget exchanges. So we tried contact and we didn't get anywhere. So I mean, I feel like we're missing some simple piece that when it falls through, this thing will generalize, because it seems, I think part of it is related to your earlier question that once you think of the way you start Euclidean, I think if you figure out how to do the contour deformation to get here, you will figure out what the contour is to do other things as well. So look at the degree, but just what should I say? Caveat. So okay, going back to these non-Markovian modes, the logic is don't integrate them all. Compute the Legendre transform of the generating function. Okay. If this was the whole story, things would have been very simple. But you already see on the board the different polarizations of the stress tensor behave very differently. Okay. And I didn't write down this one more. This guy, Tij, is Markovian. So if you try to treat this operator en masse, different pieces of it behave very differently. So you want to integrate this out because this doesn't have long-lived modes, and you want to keep these, but these independently behave in different ways. I could say the same thing for a current. There's one the scalar polarizations carry diffusion, whereas the transverse photons are just decaying. So you need some way to decompose these in pieces that allow you to treat them independently. So again, solution is straightforward. Break up this operator into pieces. Treat each of the take the polarization label out, and treat each of the pieces. So treat Tij, T0i, and T00, which you can think of as the energy operator, the momentum flux operator, and some kind of background metric shear strain operator, let's call this Tij, as independent gadgets. However, this guy in the bulk corresponds to different polarization of the graviton. And graviton has gauge invariance. So if you just do naive decomposition into these pieces, you're going to be, so you can pick some random gauge and try to just gauge fix and piece apart these guys. What you find, and this is just technical, that it's hard to sort of go through this monodromy argument because you start seeing funny gauge dependent problems at the horizon. It has to do with the fact that if you, for example, pick radial gauge where you set the radial component of the graviton to 0, the radial coordinate in this metric is null. And so time reversal doesn't play well So you don't really get good outgoing solutions. Okay. So that kept us stuck for a while till we realized that there's a way around it, which is to not work with, not fix gauge a priori, but really do what you do in cosmological perturbation theory, work with gauge invariant variables. So, and then all sorts of magic happens. So for conserved currents, the rule is, and let me say that there are various other people who've studied these kind of problems in the literature, and they all find this problem of they work in radial gauge, they find some singularity on the horizon, and then they put some ad hoc boundary condition on the horizon to cure that singularity. Now this is just absolutely in violation of ADS CFT rules, because the only boundary conditions you're allowed to put in this geometry are at the asymptotic boundaries. So you're going to go put boundary conditions somewhere in the interior, then you're over determining a second order differential equation. That's completely meaningless thing to do. So for conserved currents, our logic is work with gauge invariant combinations. And I'll just say the answer for the stress tensor. The spin 2 piece, which corresponds to this shear strain operator, behaves like a minimally coupled massless scalar. I'm not sure whether the boundary condition that was put on the horizon was tuned to get some answer that was consistent with something else. So,
because the point, if you can recover using this boundary condition, right, then maybe there is some reason why it works.
I agree. I agree, but it's hard to pass through some of these papers to figure out what exactly has been put in and what exactly has been gotten out. So I won't make strong comments, but I certainly don't think you're supposed to put strange things on the horizon. So this is a minimally coupled massless scalar. And this is some statement that has been known for decades, that you do transverse gravitons in black hole backgrounds, they just behave like scalars. This is what people use to prove area, absorption cross section being proportional to area. And there are as many polarizations of this as in 4 dimensions, there are 2 polarizations. In ADS5, there are 2 polarizations. There are 5 gravitons, so we'll see all 5 of them. The spin 1 part, of which also there are 2 polarizations, corresponds also to massless scalars. But they don't have a canonical action, but they have some power law term here. So in 2 dimensions, in ADS4, it's 1 minus d, so it's r. So the kinetic term is modified, but in a very simple way. It sort of goes to 0 at infinity. The spin 1 guy, spin 0 guy, there's 1 polarization. This also is a massless scalar, and it gave us no end of grief, but it has a similar we just write it. Some power law here, there's some other power here which I'm forgetting, but I want to emphasize this function down at the bottom. So this one was massless scalar, so it didn't do anything fancy. This was like a massless scalar, but the potential, if you look at how the potential behaves as a function of the radial coordinate, the massless scalar has no potential, so so this is some V of R roughly, but this guy has a potential that goes to 0 at infinity. Which means these modes don't really want to fall into the black hole because they have no penalty to stay at the ADS boundary. They don't behave like regular fields in ADS because this piece sort of dampens the harmonic potential of ADS. Same thing we hear, this power law, I don't remember off the top of my head, but this is sort of canonical picture for this non-Markovian behavior. Okay, so this story we worked out in a couple of papers for the stress tensor, one with people here, Joel, Akhil, Vishal, and Siddharth, and we worked out the sound mode with Julio and our other postdoc, Temple and Akhil. You can play the same game in more complicated things like charged black holes, Rice and Nordstrom, and there things are a bit more complicated because there's a mixing between the stress tense and the charge current, but you can decouple them and you can again classify things this way. But the operative point stands that things that are Markovian in general have potentials that prevent them from getting to the boundary. And so they just fall into the horizon and decay on thermal timescales. But things that are non-Markovian are so floppy near the boundary that they want to reside there and never fall in. That's the origin of their long-livedness. And this is very clear in these gauge invariant variables. Moreover, because these things are floppy, it doesn't make sense to turn on sources for them because the source, the non-normalizable mode and the normalizable mode get flipped. Okay, the way it works in practice, if you work through the details, which is the part that has never been, that we had to work out, which because it doesn't exist in the literature, this decomposition is known. This decomposition was known for nearly 2 decades, thanks to work of Kodama and Nishibashi and other people. But nobody worked out the boundary terms. So it turns out that these guys are not quantized with standard Dirichlet boundary conditions. They actually have boundary terms which make them Neumann. So they have bounded derivative terms in the boundary. And that takes some working out because these change of variables to get to these gauge invariant guys is complicated. But then you can show that it works. But you see, to compute the generating function, you want to quantize these fields with Neumann boundary conditions, keeping the Neumann boundary term. But I told you that you don't want to compute the generating function, you compute the Legendre transform. So the Legendre transform adds back field times conjugate momentum. It precisely removes the Neumann boundary term. So if you naively take all of these guys and compute them with standard Dirichlet boundary conditions, double Dirichlet problem, you get local answers, except that here you should compute them as local answers for the right and left sources, whereas here you should think of them as computed in terms of right and left webs for these boundary fields, the energy field or the momentum flux field and so on. And that gives you sensible local answers that you can study. Okay, so we managed to do this at the level of the 2-point function. And to test whether our logic is correct, we cooked up a simple toy model where we can do analytic calculations. So that basically taking this intuition that you can put in power laws to modulate whether something is long-lived or short-lived. So we just studied a toy model in the paper that's upcoming with Julio of putting in BTZ. So you put in some massive scalar and modulate its kinetic term with a power law. As a function of the power law, you see various behaviors, some funny things as well for some choices. But you can compute the correlators exactly. You can see as a function of the modulation when you get long-lived modes and when you get short-lived modes. So you can play this game. But you can also get something else which is very nice. You get a prediction for what is the analytic structure for the thermal correlators. So I told you in this picture what was the analytic structure for retarded Green's functions, 2-point functions. Until recently, I didn't know what analytic structure was for higher point functions at finite temperature in strongly coupled field theories. Now I do. Turns out that if you work in this FP basis, you only get quasi-normal poles. So F you should think of as retarded and P you should think of as advanced. Corresponding to every F insertion, you get quasi-normal poles in the lower half plane because of retarded response. Corresponding to every P insertion, you get corresponding quasi-normal poles in the upper half plane corresponding to advanced response. And in addition, you may get quasi-normal poles in the factorization channels when two F's come together and go into somebody else. So if you're doing a 4-point function like F, F, P, P, this factorizes into F, F, P, F, P, P. So this is like an exchanged operator. So this is some kind of thermal OPE. And now you can have in this exchanged momentum, which is the sum of these two momenta, you have quasi-normal poles in the corresponding retarded place in the lower half plane. Okay, so this is the entire structure up to the fact that in these exchange momenta, you can also have singularities at Matsubara frequencies. In addition to non-trivial quasi-normal modes, you can also have poles exactly at integer multiples of 2 pi orbit. And this seems to be a robust prediction that comes out straight from the analysis of correlators, and we have some general statements which we tried explaining that you can read about in the paper that should come out sometimes. So this I find quite satisfactory because it tells you that A, the quasi-normal modes are really like the physical fields that sort of in this and the sort of they can really think of them as single particle field, 2 particle, 3 particle states in the thermal state, and their weights and the residues basically is all that you really need in this problem.
So there are no branch cuts.
There are no branch cuts because we are at strong coupling. So it's true that if you were doing this at weak coupling, weakly coupled thermal field theory, you see branch cuts all over the field from multi-particle thresholds. But already it's interesting that this was known for nearly 3 decades that 2-point function just have this. Yeah, but there are no branch cuts even at higher. Yeah, yeah, and in some sense, in fact, the really nice thing in the way we figured this out is that when you do these diagrams, you can see that the ingoing propagator, bulk to boundary propagator, has quasi-normal poles. The outgoing bulk to boundary propagator has anti-quasi-normal poles in the upper half plane because it's like advanced guy. The bulk to bulk has bit of both because it's bit of retarded, bit of advanced. So now it's just a matter of taking the answer, keep factoring out the boundary pieces and leaving some radial integral to do. The radial integral you can just work out. You can show. I never said this, but all the radial integrals you have to do, these contour integrals, because they are discontinuity integrals across some cut. You can collapse them into an integral along the real line of some discontinuity. So that's the full structure of the holographic calculation. Okay. Of course, how much you can do very much depends on computing the ingoing propagator analytically. That's why we had to cook up this toy model to figure out how to do that calculation. Yeah, so there are many other things we want to do, which is to basically upgrade the toy model to actually compute non-Gaussian features of density correlators and so on, and understand how we can use this to, for example, answer Surat's question, to go beyond Schwinger-Keldysh, but that's a story for another day. I think I'm pretty much on time, so I'll stop.
So this is for the short shell kind of geometry. If you had a curve like geometry, there's a corresponding complexity.
Yeah, so we've done two examples so far. So I'll tell you one more fun thing. So we did Schwarzschild and we did Rice-Nordstrom. I'm not a big fan of rotation, but so Rice-Nordstrom has another inner horizon. So it has another cut running from R minus. But there's something funny. If you actually go away and work out all these guys, you find that there's another special point in Rice-Nordstrom. In fact, you can write the metric in a very particular way. I'll tell you what it is. There's another locus here. We'll call some charge radius. Actually, let me call it the conductivity radius. So it always lies between inner and outer horizons. It's not visible in the metric, in an obvious way, but it controls. It actually controls the charge DC conductivity of the boundary theory. So, in fact, I can tell you the Rice-Nordstrom function. If you take its derivative, this is some power law in R times this radius. In radius 4, this is how it shows up. So there's some kind of pole here, and some of these Markovian guys, these non-Markovian guys diverge there. Yeah.
As an structural extremal limit also.
Good question. So in the extremal limit, typically what you would expect is that R minus coalesces with R plus. So, and usually what would happen is everything I said would break down, because my statements relied on the fact that the horizon was a regular singular point. So the monodromy was R minus R plus the I omega.
Not exactly the extremal point, but
Near extremality, yeah. So at extremality, that because of confluence, that's not a regular singular point, it's an irregular singular point, and the solutions are just different.
But even at the regular extremal point, it's not really that R minus and R plus concept.
No,
light crossing time, it's not finite.
I totally agree. So there's finite distance between the inner and outer horizons, but at the level of differential equation, the singular points coincide. You get a double zero, right? The double zero basically means the whole structure of the.
But double zero is in the wrong coordinate system. The coordinate system itself is a change your coordinate system, then it's not a double zero.
So if you do what you've done, which you dissolve it a little bit, then it's not a double zero, and then the question is valid. But then what happens is that these distances are some distance of order epsilon. There's some regulator, which is the regulator you put in, and these are both all set on that regulator scale.
Well, you don't really need regulator, right? That's it. I'm saying it's not that this separation is remaining going to zero as regulator goes to zero. But once you change the coordinate system, then you can take the regulator to zero, metric remains perfectly finite in that coordinate system.
I was in ingoing coordinates, so
ingoing coordinate, I don't know what happens, but I mean, there's a way to change it. Introduce coordinates.
Yes.
So that now if you take the actual extremal limit, you still see two separate limits.
But Ashok, is that different from taking the ADS2, global ADS2 and taking a Rindler patch?
Yeah, I think it's similar.
So if this is similar, then I would have said that that's like regulating a little bit.
No, because the temperature is really zero. You're not regulating.
You're not regulating. Okay. Yeah, this has a temperature because it has a Rindler temperature of this ADS2. This is some 2 pi temperature. Yeah.
Asymptotic observers would want to regulate zero temperature.
Right. Yeah.
Temperature, of course, in flat space also you'll get.
Sure. So but that will be one way to regulate, but that you don't want to do that. You want to say that there's a way to do the ingoing coordinates so that you don't see a double zero. I don't know how.
The ingoing coordinates what happens.
Yeah, because in ingoing coordinate the metric is just what I wrote before, so it's just r squared f dv squared and 2 dv dr, and nothing happens. because this function just picks up double zero, and that's the problem. Do you know?
Yeah, I guess the question is that, I mean, the whole prescription is very tight to ingoing. If you
It is true.
If you kind of change ingoing, it's not, since it's just a prescription, we do not know quite what to do.
Yes, maybe I should answer the question for Surya for posterity, that because it's tight ingoing, the continuation from Euclidean is a bit tricky.
So I guess, you could change the coordinates, but then you have to
Redo the prescription.
redo this monodromy analysis and all that, and try to see whether you can still solve a double Dirichlet problem.
Yeah. So your picture is in Schwarzschild coordinates, where you sort of go from.
Yeah, it's Schwarzschild, but
Then you rescale. So yeah.
So that as you take the Pythagoras to 0 limit,
Then you get something regular.
you still have a finite metric.
Right.
Then in that metric, that's your split.
Right.
That 200 split.
Yeah. Yeah, I mean, there's an interesting question in that context, which doesn't really fully. Yeah, I'll postpone it. I'll tell you later. It is interesting to ask what happens to quasi-normal modes as you take the extremality limit. I mean, people have studied them in the past, but I'm not sure how to fully tackle it in this context.
I guess the final question is to, mathematically write down a differential equation which has a double Dirichlet, well-defined a double Dirichlet problem.
Yeah.
So that you can give sources and then you can get a solution.
To vary and get them. Yeah. So going back to your question, Rajesh, if you want to do curve, I don't think there's a problem. I mean, at least non-extreme curve. I think. No, if you think of it as a contour prescription in this variable, I think it doesn't matter.
There's a way of doing it, which Ashwin and Vidisha worked out. Yeah, so it just becomes complex, and there are various i's at various places, and you get various omega, which are the rotation.
Yeah.
Yeah, I mean, the radial thing I can kind of see with some radial one.
Yeah.
The geometry is what I was trying to see. I don't know how
yes, how to draw a picture of that. Yeah.
So, but you can define. There will be.
There's a sensible ingoing chart, and therefore there is a way to go around the cut. And the monodromy is exactly the same monodromy, because it's just set by the local temperature, at least for spinless fields. Fields that carry spin will see slightly different monodromy because they'll pick up monodromy from the angular momentum. Well, obstruction in the sense that I have not been able to write down a coordinate, a simple coordinate under contour prescription. Okay, so, but you don't need one, because even here, in fact, you could have just said, I have 2 copies, and I just need to tell you how to go from this copy to that copy. So for the OTOs, you could work out that kind of rule. 4 copies, and so exactly. But each time you cross some, so it's easy enough to draw. Let's say we want to do this contour. So you have 4 folds, and so you have this guy, and actually you go in through here, emerge here, you go out here, come back here, you fall in here, and you come out there. So 1, 2, 3. So I just need to tell you what happens at every crossing. So I can tell you what happens at every crossing. 2-point functions, I think we all know how to get, but we don't know how to get anything. Try to compute anything else from it doesn't seem to make sense. We don't get connected correlators. But we can speculate that maybe there's another geometry, but which computes connected guys, but this gives you the disconnected pieces. But that's just speculation. Or maybe we just are not doing the calculation right.
Are there any questions online?
Okay. So then let's try to